and the class number 1 problem for families of real quadratic fields. Okay.
So thank you for the introduction. I'm very happy and honored to be here. The conference is it's been great so far, and will probably still be great. So I'm going to discuss the class number 1 problem for certain families of real quadratic fields, and everything is joint work with Henri on Zoom. So the class number 1 problem goes back to Gauss, where he conjectured the list of negative class number 1 discriminants in a slightly different form. He only had fundamental discriminants, and also his definition of quadratic forms was a bit different because he needed the middle coefficient to be. But he more or less conjectured this. And then this was proven by Heegner, Baker, and Stark in the 60s. Heegner and Stark gave more or less the same proof, and Baker gave another one. But all of these proofs made a critical use of the theory of complex multiplication. And so the goal of this talk is to explain how Henri's conjectural theory of real multiplication lets us do the same thing for certain families of real quadratic fields for positive discriminants. So the main theorem we have is well, assuming Darmon's Henri's conjecture on Stark-Heegner points that I will recall next, we can solve the class number 1 problem for these families of discriminant of the form n squared plus or minus 4. I'll explain where these families come from next. But this was actually proven unconditionally for fundamental discriminants by Biro in 2003 and Bion in 2007 with the same method, adapting the method of Biro, with a completely different method. And I will say almost nothing about this, but basically you take the zeta function of the quadratic field and you twist it by some character of prime conductor Q. And you have a factorization in terms of L function. So you get an explicit description of this value at 0 as a product of 2 special values of L functions. And on the other hand, you can also write it as a sum of ideal class zeta of partial zeta functions. And Biro gives an explicit formula for the value at 0 of let's say the partial zeta function associated to the principal class for these discriminants. And so if this class number 1, there's only one partial zeta function. You get something, an algebraic number is equal to a product of 2 algebraic numbers, basically, and then you do some congruences. There's no analysis. It's a very interesting proof, but it seems different, very different from ours. And it only works for fundamental discriminants. This also works, both of these methods work for slightly more general families of discriminants, but this is the simplest case. But it's funny that they seem to work for exactly the same families of discriminants. Although then Biro did something, there's another paper with Lapkova, where he somehow manages to treat multiple families at once, and we haven't been able to do it. So that's it for the introduction. And one last thing I want to say is why we should expect these families of the form n squared plus or minus 4 to have growing class number. So that why should we expect there to be finitely many class number 1 discriminants? Because if we consider all positive discriminants, then we expect there to be infinitely many class number 1 discriminants. And this is due to Siegel's theorem, which says that the class number times the regulator of a quadratic field has more or less size square root of the discriminant. So then when the discriminant is negative, the class number grows to infinity. And when it's positive, the same thing holds, provided that the regulator is not too large. So for instance, if the fundamental unit has polynomial size. In our case, it has size square root of it. Well, that's already a great theorem, but the issue is that It's not effective because it relies on, because you need to distinguish the case where there's a Siegel zero and where there are no Siegel zeros, and so it's not effective. And so that's why we proceed via real multiplication. So now I want to recall some facts about complex multiplication before moving on to real multiplication. So start with an elliptic curve over Q of conductor N. And for simplicity, we assume that E is semi-stable. So its conductor is square free, and that it's unique in its isogeny class over Q. So in particular, it has a trivial torsion over Q. And then the modularity theorem of Wiles and Taylor-Wiles gives us a modular parametrization. So that's a dominant map of algebraic curves over Q from the modular curve to E. And analytically, this is very easy to describe. It's using complex uniformization. It's just given by integration against the cusp form attached. But now, as Mike said yesterday, on the modular curve, we have a large supply of algebraic points which are these CM points, and we can map them into E to get algebraic points over E. So more precisely, if D is a negative discriminant where N splits in the quadratic field, then there are, under this condition, there are CM points of discriminant D in X naught of N. And we can map those into E. And these points are all defined over the ring class field by the theory of complex multiplication. And these points Pi, by the Shimura reciprocity law, they're uniquely determined up to conjugation, to Galois conjugation, and to sign possible. So if we take the trace over Q of square root of D, they're all conjugate over Q of square root of D up to sign, we get a well-defined point up to sign on E. And this relates to the L function of E via the Gross-Zagier formula, which says that, well, the derivative of the L function at 1 over Q of square root of D is up to an explicit non-zero fudge factor, the height, the Néron-Tate canonical height of this point PD. So as a consequence, we know exactly when this point is torsion, when the derivative vanishes. So if we do this in reverse, we can start with an elliptic curve of analytic rank, say 2. And then this derivative is necessarily 0. And so the point PD is torsion. So PD is a torsion point over a quadratic field. But any elliptic curve over Q has torsion growth over only finitely many quadratic fields. So since it has trivial torsion over Q for almost all discriminants, it must have trivial torsion over Q square root of D, and so this point must be 0. And now, in the case we're interested in the class number 1 case, well, there's the Hilbert class field is just Q square root of D, the ring class field. And so there's no trace to consider anymore. And this Hegner point is just the image of a CM point of on the modular curve. And so if we do this, if we go backwards, we could, in theory, find those class number 1 discriminants by computing the fiber of, by computing the pre-image of 0 by the modular parametrization. There's a caveat though, because we had this assumption that N needs to split in Q square root of D, this Hegner hypothesis. And this actually only finitely many discriminants satisfy this, because if D splits, sorry, if N splits, and if a prime splits, it needs to be a norm because it has class number 1, and then this automatically implies that it's greater than D over 4. So the takeaway is that small primes tend to stay inert in class number 1 imaginary quadratic field. And this will also be true in class number 1 real quadratic field. I should mention though that there's a way to bypass this, which is to, instead of using a parametrization by a modular curve, we could use a parametrization by a Shimura curve. And the hypothesis becomes that N needs to be inert. And then we still need to compute this fiber, but we can do this using p-adic uniformization of Shimura curves. And so this is work in progress, by which I mean that I did the computation and they seem to work, but I did not I haven't written down anything yet. But the computation is very similar to what I'll explain in the recurring case. So let's move on to the definition of these Stark-Heegner points. So the first thing we do is construct an analog of this modular parametrization. And using complex uniformization of modular curve and of elliptic curves, we can view this modular parametrization as some analytic function over the upper half plane, which is invariant under gamma naught of n acting by Mobius transformations up to this lattice of E. And this function is given as integration against the cusp form. And now in the real quadratic setting, we're going to try to play the same game. So the first thing we need is to have a complex uniformization for elliptic curve, p-adic uniformization. So we pick a prime of multiplicative reduction, and we have the state uniformization. And I'll let M denote the prime to P part of the conductor. And then we also need an analog of the upper half plane, displayed by the Drinfeld upper half plane, p-adic upper half plane. So it's a rigid analytic space whose CP points are canonically identified with a P1 of CP minus P1 of QP. So if you do this over R, you get the upper half P1 of C minus P1 of R. That's the upper half plane and the lower half plane. But p-adically it's connected. And yeah, in this talk I'll identify many rigid analytic spaces with their CP points. And then the analog of the modular parametrization, this time it's a one cochain, one cohomology class, but then this thing is the same thing, but in multiplicative notation. So we have a cocycle taking values in the space of invertible analytic function on HP, modulo this state lattice, state period. And it's a cochain for this group, gamma naught exponent P of M, acting by Mobius transformation. And this is defined exactly as gamma naught of M, but you take matrices in the Hara group, so with coefficients in Z adjoining 1 over P, instead of just and I will not recall the definition of this one cohomology class Che, but I'll recall some of its properties. Well, the first one is that it's parabolic, which means that when you restrict it to upper triangular matrices, it becomes trivial. It's a co-boundary. And that's nice because parabolic cocycles have an easier description in terms of modulo symbols. The modulo symbol is basically an abstraction of the notion of an integral with endpoints in P1 of Q. So it satisfies these two transitivity relations that any integral satisfies. Like when you integrate from R to S and then from S to T, you get the integral from T to from S to from R to T. And this is and it needs to be invariant under our group gamma naught of M. I would just say gamma naught of M because it's shorter. And so once we have a modulo symbol, the way we get a cocycle from this is that we fix a base point T naught. And then we define the value of the cocycle at an element gamma, the value, the modulo symbol from T naught to gamma T naught. So it's like when you integrate a differential form from a base point to gamma times this base point, you get a cocycle. And this is if you pick another base point, you multiply this by a co-boundary. So this is, well, the cohomology class is well defined. And in fact, our module, so now I'm going to view the cocycle JE you alluded to in the previous slide as a modulo symbol. And then as a modulo symbol, it turns out that it's given, which just means that it's also invariant under matrices of determinant -1, not just 1. And the reason for this is that basically there are two cocycles we could have considered, and one would have been and this one is even and the other one is odd. But the odd cocycle will produce points defined over the narrow ring class field, and this one produces points over the wide hill ring class field. And well, we want to use things with class numbers and wide class numbers, not narrow class. Okay, so we're almost, so now we can define Stark-Heegner point. So we pick an Rm point in the upper half plane. So that's just a point which generates a real quadratic field. And such that M splits in this real quadratic field. So that's the Heegner hypothesis that we already had in the imaginary case. And this is this special point that Mike talked about yesterday. And then we can consider the ring. So it's special in the sense that the ring of matrices, which are upper triangular modulo M and its coefficient Z at 1 over P, that fix it. It has rank 2 as a Z adjoint 1 over P order and not rank 1. And so you can view it as a Z adjoint 1 over P order in Q of tau by just, well, you take a matrix and this matrix fixes tau by Mobius transformation. So the vector tau 1 is an eigenvector. And then you can map the matrix to the eigenvalue, which is C tau plus. So this embeds this order in Q of tau, and this is a quadratic order in Q of tau. So we can consider the stabilizer under this group, gamma not tilde, which I defined previously. And this is identified with via this embedding with the group of units of this ring O tau. And so by Dirichlet's unit theorem, it has rank 1. It's a group of unit in a real quadratic order. So we can pick a generator gamma tau, which I call the fundamental automorph of tau. And we can also make it unique by normalizing it so that it's greater than 1 when you embed it into Q of tau, but it's not so important. Well, that's a well-defined object. And like this is like tau is fixed by this torus, which is norm 1 units in this real quadratic field as in Mike's. And then once we have the automorph, we define the Stark-Heegner point as, well, so the Stark-Heegner point attached to tau is you take the automorph and you evaluate the cocycle at this. So this gives you a function. Then you can evaluate the function at the point. And this gives you an element of CP. Sorry. And this is well defined. It only depends on the cohomology class. And it's also invariant under gamma not tilde. And the main conjecture is that these behaves exactly like Heegner points. So the CP point of E is actually defined over the ring class field H tau. And we have a Gross-Zagier formula, which takes the same form as before. So the height of this point relates to the derivative. And so as before, we conclude that if tau has class number 1 and E has analytic rank 2, then the Stark-Heegner point is trivial. For almost all tau, but in fact for the ellipticals we will consider, this will work out for every single. That would be not.
By rank, you mean rank over Q, right?
Yeah, yes. Because then we're varying this tau and we want this to be always 0 for any. So we want to solve this equation, but this is not really this is not an analytic function. An analytic function divided that tau is a cocycle. So this seems hard to solve a priori, and we cannot solve it because there will be infinitely many solutions, since there are infinitely many positive. There should be infinitely many positive class number 1 discriminants. And so to summarize what we did until now. So we start with so sorry, not here, it's not a summary yet, but when we were doing this in the imaginary setting, we were annoyed by this Heegner hypothesis because small primes are inert and not split. But this time we can make the Heegner hypothesis disappear by just setting the prime to be part of the conductor to be 1. So this just means that E has prime conductor P. And then, so in this setting, a Stark-Heegner point is defined for any real quadratic point tau in CP, which belongs as long as it belongs to the upper half plane. And so that means that it doesn't belong to QP. And so that just means that P is inert. Sorry, that P doesn't split in Q of tau. And that's great because, as I keep telling you, small primes tend to stay inert. And so more explicitly, we can prove this lemma that any prime less than n minus 2 is inert if this has class number 1, or it divides the conductor. But this is very elementary. All right, and now the second ingredient we need is some way to better compute the Stark-Heegner points for these discriminants. And the key lemma is that actually the Stark-Heegner point attached to the principal, the fundamental unit, is just given by the evaluation of a single rigid analytic function that doesn't depend on D at this quadratic point. So epsilon D here is the fundamental unit, and it takes this very simple form. And well, actually, this is completely trivial to prove because we have a super simple description of the automorph, since D is so simple and the fundamental unit is so simple. It's just given by this 2 by 2 matrix n plus or minus 1, 1, 0. And this n 0 to plus or minus 1 divided by 0, so to infinity. And so when we evaluate the co-cycle, so the Stark-Heegner point is just defined as the modulus symbol evaluated from 0 to gamma 0, so that's infinity, and then evaluated at epsilon, so that's just phi of epsilon. So that's much better because now we just need to solve a single equation, an analytic equation over HP. And now is a summary of our strategy. So we start with some elliptic curve of rank 2, and in fact, most will work for this. Most will work of rank 2 over Q, conductor P, and which is unique in its isogeny class. And we've reduced the class number 1 problem for these discriminants, which do not have conductor divisible by P, just because of this lemma. If the conductor divides P, we don't know if they belong to the HP. To solving the equation phi of tau equals 1, mod Q to this. But there are still a couple of reductions we can make, because first of all, we do not care about all the points tau. We just care about the points where tau must be quadratic. I mean, tau is actually quadratic over QP. It belongs to the, since P is inert, it belongs to the unramified degree 2 extension of QP, which I call QP squared. That's the first thing we can say. But the second thing we can say is that it's not any quadratic point in HP. It belongs to a standard aphenoid, which means that when you reduce it mod P, you view it as an element of P1 of CP, and you reduce it mod P, you get something in P1 of FP bar. And this is not in P1 of FP. This is how the standard aphenoid is defined. So the points that do not belong in P1 of FP mod P. And that's just because, well, we have this square root here, and when you reduce this mod P, the square root stays. So it belongs to the standard aphenoid. And this is already much better because this standard aphenoid, it's an aphenoid, so it's compact. And so now the image of the standard aphenoid by phi will be bounded. And so this ambiguity is not annoying anymore. And in fact, we can even remove the ambiguity completely because it turns out that we can normalize phi to map the standard aphenoid to p-adic units. And then there's no ambiguity anymore. We just want to solve the equation phi of tau equals 1.
Can I ask? So
Yeah.
a priori tau could be ramified as well, but you probably exclude that by genus theory or something.
No, we will use genus theory, but right at the end. So for now, we're assuming that the conductor is not divisible by P. And then if n is sufficiently large, P needs to be inert.
Sure.
Yeah. We're assuming that the conductor is not divisible by P. And so now the way we usually solve equations with p-adic analytic function, the way we find zeros of p-adic analytic function is, for instance, to use Hensel's lemma and to look at the reduction. And so Hensel's lemma tells us that, so yeah, so the reduction of, so we can reduce phi e. Phi e is a function, so we restrict phi e to the standard aphenoid, and then we reduce everything mod p. So a standard aphenoid, it gets mapped to this algebraic curve over fp bar, let's say. So p is p1 minus the fp rational points. So phi e gets mapped to a function over this algebraic curve. And that's just, this is the ring of function on the algebraic curve. You need to invert x minus a for any a in fp, and so and also it should also be a unit because phi is invertible, so re is invertible as well. And then Hensel's lemma tells you that, well, you just need to find the zeros of the quadratic zeros of r minus 1 to get the quadratic zeros of phi minus 1. And in fact, we don't need Hensel's lemma because Hensel's lemma tells you that you can lift these zeros when you don't know what the p-adic zeros actually look like. But in our case, we already know the p-adic zeros, so this is even more trivial than more obvious than Hensel's lemma. So now what we need is a way to compute this function re. And well, this proposition, which follows from the definition of the co-cycle, which I haven't given you, but it's very explicit. There's some constant which is totally explicit. And in fact, in our setting, it should be 1. We have reason to believe that for rank 2, curves with rank at least 2, this constant should be 1. And then you take a product of x minus a, and the exponent, the order of a, is given by the even modulo symbol attached to it. Well, you don't need to really understand this formula, but it exists, and it's like this is all implemented in Sage, and we can compute this in a very short, with very few lines of code, very short amount. So now let's do the computation. Well, I'm not going to show you computation, but I'll just show you the result of the computation. So let's pick the smallest elliptic curve of rank 2 in prime conductor over Q. So it has conductor 389. Then we factorize r minus 1. And we obtain lots of degree 1 factors. And well, we don't care about those, so let's ignore them for now. And then we have 6 quadratic factors, and they have the form x squared plus or minus nx minus 1. So that's the minimal polynomial of epsilon d or minus epsilon d, depending on for n when n is 2, 5, or 7. And these are all the class number 1 discriminant of this form n squared plus 4, where 389 is inert. Get the same thing for the discriminants of the form n squared minus 4. I should remark here that we have n equal 1 as well, which is negative, and it's 1 squared minus 4, it's minus 3, and we get something cm actually. But this is kind of a degenerate case of the theory, so it's fine. And in this case, we can even prove unconditionally that it's a 0. And then we have some larger degree factors. And the conclusion, well, is that so this there's no theorem. This proves our theorem for discriminants which do not have conductor divisible by 389. And if we want to remove the condition on the conductor, we just need to do this with another prime, let's say congruent to 1 mod 4 again. So for instance, 433. And then this proves the theorem for discriminants which do not have conductor divisible by 389 times 433. But if a discriminant is divisible by both 389 and 433, it has even class number by Janus theory, and so it cannot have class number 1. So this proves our theorem. And I just want to end with one question. So we had 66 zeros defined over FP, which is almost half of the zeros. And in fact, this holds true for Well, for every rank 2 or rank 3 curve that we tried with, so we did that with all rank 2 curves of conductor less than 10,000, and we always had like 50 or 100 or 150 zeros defined in FP, which is somewhat mysterious considering that these zeros don't lift to anything in the standard affinoid. Yeah, so well, it would be interesting to explain those zeros. And actually, when we do this with Shimura curves, so the strategy is the same. We reduce something mod p and we find the quadratic zeros. And there are also like 50 or 100 zeros defined over FP, even though they don't lift to anything in the standard affinoid. But for Shimura curves, we have more tools and they seem less mysterious. So maybe this will give us an idea of where these zeros come from. Thank you for your attention.